So I'd like to talk a little bit about these types of friction problems that we discussed in lecture. I just want to clean up some potential misconceptions or just talk about how we would generally set up these problems. So I've got 4 different examples up on the whiteboard. So we've got 3 different problems that I would call the general ladder type problem, but that's just a general term for it. It could apply to other types of frames and machines as well too. And then we've got another example that's similar to what you have on the homework. And fundamentally, this type of problem still fits within the same kind of categories. It's simply a frame or a machine with interfaces that can have a friction force on them, and we deal with them basically the same way. So let's just kind of set up what the Freebody diagram would look like for each of these and talk about how the problems are potentially different. And so looking here at example A, we have a ladder or just a single frame, a straight frame, and it's supported by a roller at B, so no friction at B, simply a roller that's preventing it from moving left and right. And then we have a friction surface at A and some sort of coefficient of static friction at A as well too. So with a problem like this, the given information that we have are the support conditions. We know roller, we know friction surface, we know the geometry as well too, the angle of this, and we would also know what the length of this frame is. We're given what the coefficient of static friction is, and we're given the weight. And the call of a question like this might be whether or not the ladder is slipping at point A. And so this is the kind of a problem where you would simply check to see if slipping is occurring, but other than that, actually calculating the horizontal force at A would not be by using mu. We wouldn't be calculating the normal force at A and then calculating the maximum friction force. Here, we would calculate the actual horizontal force at A and just check and make sure it's not slipping. So our free body diagram for something like this would include the ladder itself. We have the applied load W acting at the centroid of that member. We've got a vertical support reaction at A. I'll call that N sub A. We have a horizontal support reaction at B. I'll call that N sub B due to this roller. And then the other bit of information that we need to know is what is the friction force at A? What is that horizontal reaction? And again, we would know all of the geometry. It's given in this problem. The angle, we would know the length of this as well too. And so really the only unknowns that we're talking about here are the reaction at the roller at B, the normal force, the vertical reaction on this surface at A, and then the horizontal reaction at A as well too. So if you think about it this way, we have 3 unknowns, and statics alone with a free body diagram like this will give us 3 equations just based off of equilibrium itself. So I have enough equations with statics to solve for all 3 unknowns. Once I've solved for the unknown, the horizontal force at A, and I've solved for the normal force at A, then all that I would do is simply check and make sure that FA is less than FA max. So this would be kind of our first step, would just be solve for all the forces with equilibrium. And then the second step would be use our equation to figure out is FA less than or equal to, mu sub A times the normal force at A. So this is where our friction step is at the end, just to check and make sure that slipping is not occurring. Now, in these other problems, we're going to have to assume that slipping is occurring, but these 2 problems are slightly different. And I somewhat kind of butchered the description of this in lecture, so I want to make sure that everybody's on the same page. So this is a very similar problem, but now we have a support with friction at B, a support with friction at A, and just like before, we know what the geometry is, but here, instead of giving us the weight W, it's asking us to find what the maximum weight of the ladder could be in order for this to not slip. And so failure would be slipping of this frame. And the key about this type of a problem, and your book discusses this as well too, is that in order for point A to slip, point B has to slip as well. And so with a problem like this, because this is a rigid member, all points have to slip at the same time or not at all. And so with a problem like this, let's just talk about the free body diagram. We know that the maximum value of W will be whatever is required to start points A and B to slip. Whereas with this problem, we didn't know if slipping was occurring or not, and we didn't really find out until the very end. Here we have to assume that slipping has occurred in order to get enough equations to solve for all of our unknowns. So we can figure that out just by looking at the free body diagram. So just like before, I've got the rigid member here. I've got some weight applied, and again, we don't know what that is yet. We're trying to figure it out. I do have the geometry in this case. I have theta. We're assuming that we have all of the lengths as well too. And now my normal forces, just like before, 1 at B, 1 at A, and we need to prevent slipping, and I'm going to assume that this is rotating down, meaning that this is going to slip to the left, which means that the friction force is going to be resisting that, pushing to the right. Here, if this is slipping down, then the friction force has to be going up, and I'll show that F sub B. So in this situation, I really have 5 unknowns. So we don't know what W is. I know what theta is. I know what my geometry is. None of that is an unknown, but I don't know the maximum weight of the ladder. That's one of the things that I'm trying to answer. I don't know quite yet what the friction force at A is going to be. I don't know the normal force at A. I don't know the friction force at B, and I don't know the normal force at B either. And so really we have 5 unknowns. And I can only deal with 3 of those with statics, because I have 3 equations of equilibrium. It's a 2-dimensional problem. The sum of the forces horizontally, the sum of the forces vertically, and the sum of the moments, but that's the only 3 equations of equilibrium that I have. Now I will get 2 other equations due to mu times normal force. This is our definition of Coulomb friction, and because W max that I'm solving for occurs when A and B slip at the same time, I can simply rewrite the friction force at B as the friction force right before slipping occurs, which will simply be mu sub B times NB. But we know that B can't slip unless A is slipping, and so the same thing, the friction force at A will be equal to mu A times NA. This is what we call multiple points slipping at the same time, and so because they're slipping, or again, we call it right on the verge of slipping, that means I can set them to their maximum values. So even though I had 5 unknowns, my definition of what the force right before slipping occurs, that Coulomb definition of friction, I can plug those in, and now I have 5 unknowns, but 2 of them are dealt with by Coulomb friction, and then 3 of them are dealt with by statics, our equilibrium equations themselves. Once we have that defined, then we can solve for all of the unknowns, and then eventually get back to the call of our question and solve for W. So it's all a matter of how many unknowns do I have, how many equations do I have. It's just that some of our equations will be due to statics, some of our equations will be due to the definition of Coulomb friction. Okay, so like we said, with this problem, B, if it's slipping, means that A has to be slipping as well, and vice versa, because they're connected with this rigid frame element. Now, the third example, example C, is a little bit trickier. So with example C, it's a similar idea in that we have a ladder. It's just that now we have a pin, an internal pin between the 2 of them, and it's asking us to try to find the maximum horizontal force P in order, the maximum force meaning the force before either the support at A or the support at, in this case, C now, is going to slip. So what value of P is the maximum before A or C slips. And the big difference between this problem and the previous problem is that with example B, both of the supports have to slip at the same time. Whereas with this example, either C or A could slip independent of each other because they're not attached completely rigidly, but because there's a pin in between. A could slip separate of C, and then that wouldn't necessarily mean if A moves over 1 inch, it doesn't necessarily mean that C is going to move over 1 inch. Whereas if this were to move or rotate, the other one would have to move or rotate as well. Here, because they're free to rotate about these points, C might stand still, this whole thing might rotate up, this hinge would move, but it's not on a friction surface. And so if A moved over 1 inch, B might move up and over to the right, and then at C it just might rotate. So in this case, we can't rely on assuming that A and C are both slipping at the same time. They might slip independent, which isn't really too much of a difficulty to solve for. It just means that we need to look at both cases independently. So if we were to look at our free body diagrams, I'm going to make a section cut through B, and I'll look at a free body diagram of member AB, a free body diagram of member BC, and when I do that, we know that the internal hinge here at B can support a horizontal force and a vertical force. So I'll just draw those BY, BX, and it's the same equal and opposite force on the right side. So there's BX, there's BY. And again, I've just assumed the direction vertically and horizontally and then mirrored it with an equal and opposite on the other side. If I have the incorrect direction here, it'll just show me with the value, a negative value, which is not a big deal. At point A, I'll have a normal force. At point B, or sorry, at point C, I'll also have a normal force. We have a couple weights here. Here we're trying to solve for P. We can assume that W's, these weights of the ladders, are given. Those are not unknowns. So I have W1, I have W2, and I know that, I know that. I don't know the force applied to member BC, about 3/4 of the way up. And we can assume that we have all the rest of the geometry as well too. So I can assume that I have all the lengths of these members. I have the angle as well too. And all the distances, all the geometry that I need, I can assume those are known. So the only thing that I'm missing here is some friction forces. So friction force at point C. I'm just drawing these in opposition to the direction of the driving force. This is opposing movement that way. Same thing here. I'll assume that this is opposing the direction of the imposed force. And, minus a little bit of cleanup here in a coordinate system, this is pretty much a complete free body diagram. So I just said you can assume that we know W1, the weight of the ladder on the left, W2, but we don't know BY or BX. Those are the pin forces. And again, we show them on the right-hand side, but it's still just two unknowns. Whether we solve it on the left or on the right, it doesn't really matter. BY is the same as BY over here. I don't know NA, I don't know FA, I don't know NC, I don't know FC, and I don't know P. Okay, so at this point I have 1, 2, 3, 4, 5, 6, 7 unknowns. So I have 7 unknowns. Now fortunately, because we've split this into 2 different free body diagrams, for the free body diagram of member AB, I have 3 equations of equilibrium. So I have 3 on the left, I have 3 equations of equilibrium on the right, so plus 3 equals 6 equations of equilibrium. So just statics alone is going to get me all but one of the unknowns. So I need to figure out one more equation based off Coulomb friction. So I need one more equation based off mu times n. And the question is, well, do we select the left side to assume that it's right on the verge of slipping, or on the right side do we assume that C is right on the verge of slipping? And the question is, you have to assume both of them and do 2 different analyses, one for the left side assuming A is slipping, and then 1 assuming that the right side is slipping. So what you would do is you would set FA to NA times mu A. So you'd assume that this is right on the verge of slipping, and then assume that C is not. That would allow you to solve for P, because that will get rid of one of your unknowns, then statics alone is enough to solve for the other unknowns. So scenario number 1, assume A is slipping, set FA equal to mu A times NA, solve for P. That'll give you one value of P. Scenario 2, set FC equal to mu C times NC, solve the whole thing for P, right? You'll have a different value of FA at that point because you're not assuming it's slipping anymore, and then you'll get two different values of P. And then whichever of those values of P is lower, that will be the maximum force that this can support at this location. So P max would just be the lesser of the P required to make A slip or the P required to make C slip. Other than that, it's the same kind of idea as the previous scenario. The big difference here is that A and C can slip independent of each other, whereas example B, A and B have to slip at the same time because they're connected with a rigid link. Now the last example is an extension of the same kind of idea, because if you look at every single time we draw a free body diagram, when we have a friction surface, we simply replace or show a normal force and a friction force. And for a problem like this, kind of similar to what's in your textbook and similar to the homework, one of the homework problems as well too, here we have, I think they show like a roll of sandpaper, and they're pulling up on one side of the roll, but it's leaning up against a wall and it's being supported on a floor. In this situation, they're pulling up and they want to figure out like how much force P, or what's the maximum force P before this starts to rotate. And so it's the same exact idea. Everywhere you see a friction interface, you need to replace it, and let's draw a new free body diagram. You need to replace it with a normal force and a friction force. So here, to show all of the forces acting on this, I have P, which would be my unknown. The weight here would be a given value. And now on the interfaces, at the point A, I need to show a normal force. At the point B, at the bottom here, I need to show a normal force as well. And now, because each of these are friction surfaces, I need to show a friction force at B and at A. And again, here we're talking about rotation of this. Based off the imposed force direction P, I can assume that this is trying to make this roll of sandpaper rotate counterclockwise, which means that to resist that, I would need a friction force in the clockwise direction, because this is trying to rotate it counterclockwise. So FB, and likewise I would have FA. Now with a call of the question like this, asking for what is the maximum force that can be applied, that means this is an unknown that I'm trying to solve for. So if I were to look at this, I would say P is an unknown value. I'm trying to solve for it. Weight we have, that's just a given part of the problem. I don't know FA, I don't know NA, I don't know NB, and I don't know FB yet. Now here I only get one free body diagram, so after 1, 2, 3, 4, 5 unknowns, I get 3 equations just from equilibrium, which means that I need to get 2 more equations based off mu times n, which makes sense based off the system that we're looking at here, because in order for point A to slip and for this to start rotating, point B has to slip as well too. So the 2 equations of equilibrium, the 2 equations of friction that I'll get from this problem are going to be FA is starting to slip, which means it is equal to mu A times NA, and here B will also have to slip. This is very similar to example B, where all the points of contact have to be slipping together because this is all connected with one rigid body. If A rotates, then B has to rotate as well, and so B will also be at the maximum value of mu B times NB. So once I've done that, now my friction forces are just in terms of the unknown normal force, and I get 1, 2, 3 remaining unknowns because I've dealt with FA and FB with my Coulomb equations. And then I should be able to solve for P. Now, one thing I would mention about a lot of these problems is that once you start bringing in these friction equations, you often will have to start solving for simultaneous equations as a result, but we've already had to do that in a couple different examples. And so if you have two equations with two of the same unknowns, you can either use substitution, you could use your TI-36X Pro, or whatever other FE approved calculator you're using to solve for those simultaneous equations. But for these problems, really the most you'll have to solve for would be two equations and two unknowns at the same time. So again, when I call it a ladder problem, generally speaking, these are the kinds of scenarios that we're looking at. This one is the same idea. I get that it's not a ladder, but the points of friction being applied, the types of equations that you run are exactly the same. It's not like the belt problems or the corkscrew problems, things like that, where you need a specialized equation. For the ladder type problems, you're simply splitting them either at internal releases like hinges, and then you're making a section cut where the interface with the friction surface is. It's the same exact procedure for these, and honestly it's the same exact procedure for wedges as well too. And so the ladder type problem simply means that we're only using mu n and then our regular equilibrium equations to figure out the friction forces. We're not using a specialized belt friction or screw thread friction type equation. So these types of problems fit within that definition as well too.